Tetrafluoroethene is made from chlorodifluoromethane in this reversible reaction. 2CH, ClF2 gas, C2F4 gas plus 2HCl gas. Calculate the amount in moles of C2F4 and of HCl in the equilibrium mixture 2 marks. If you watch these specific videos on calculating moles of equilibrium mixture, you know I like to use MCE, but in this case I'm just going to do ICE because this is the original method, the ICE method. And then you can add in mole fraction, partial pressure, total pressure, etc. So ICEMP, that's what the whole thing is, not partial total pressure. So C2F4 got HCl. We're not going to include the moles of it. Just going to include the actual elements itself. CHClF2. We know a 2 mole sample of this is placed in a container of this much and heated. When equilibrium is reached, this much is made. This is how much is contained, so remains. So we've got 2 moles of here. So before I carry on, I stands for initial moles, C stands for change in moles, and E stands for equilibrium moles. And what we're trying to find is the amount of moles in the equilibrium mixture, hence the equilibrium moles. So we're going from 2 to 0.270. So what's that change of? Well, that's minus 1.73, right? Now if we're decreasing on one side, the change is decreasing on one side, the change is going to be increasing on the other side. So in this case, we're going to assume that C2F4 and HCl have 0 initial moles. And what we're going to do for HCl, because it's a 2, they both have the same mole ratio, we can also add 1.73. So we get 1.73 equilibrium moles. However, for C2F4, it's a 1, so 2 to 1. So what we have to do is we have to divide this by 2, and that's going to be the decrease. So it was still, no, we're adding actually, yeah, because this is on the same side as HCl. So we're adding, but we're not going to add 1.73, we're going to add 1.73 divided by 2, which will give me 0.865. So the amount of C2F4, 0.865, amount of HCl, 1.73. 1.865, 1.73. 2.2, given expression for Kc in this equilibrium. Well, remember Kc, square brackets, so it's going to be square brackets of products of reactants. C2F4, HCl. However, the HCl has 2 moles of HCl, so therefore it's going to be squared divided by CHClF2, and same with CHClF2, it's got 2 moles, so it's going to be squared. Question 2.3, 2.4, and 2.5. So 2.3, calculate a value for Kc. Now, a lot of students will be like, okay, we'll just remember Kc. So first things first, we need to find the concentrations. We can't just jump in and substitute the equilibrium moles. It doesn't work like that. Because then why would it be 3 marks? It just wouldn't. It'd be 1 mark. Moles equals concentration. Actually 2, because we are going to have to give the units as well. Moles equals concentration times volume. Therefore, concentration, just rearranging it, concentration equals moles divided by volume. Therefore, I'm going to need to find out the concentration of these 3 total products and reactants. So concentration of HCl equals, well, the equilibrium moles, which is 1.73, divided by the volume, and this is why it gives us the volume in the question, 23.2. We don't have to divide by 1,000 or times by 1,000 for this. In this case, it's already in its correct units, dm cubed. So it's just going to be 1.73 divided by 23.2, and obviously HCl is squared, so do need to square that, which I will show when I substitute it into the actual equation. Concentration of C2F4 is going to be 0.865 divided by total volume. Yep, 0.865 divided by 23.2. The final one, CHClF2, concentration of CHClF2 going to be 0.270 divided by 23.2. Okay, once we find out the concentrations, then we just substitute it into this equation. So, but remember, for these two, HCl is going to be squared, and for CHClF2 is also going to be squared. Then you get Kc. Obviously, I could do this whole thing substituting it, it's just going to take a lot of time. Plus, there's a lack of space as well. So, once we substitute the values in, we get Kc is equal to 1.53, and the units, I will go through the units. Well, the units, well, if you think about it, we know we're working with mole per dm minus cubed. So in the products, it's going to be mole per dm minus cubed to power 3 because we've got 2 and 1. So mole per dm minus cubed to power 3 over mole per dm minus cube squared. I'll just label this units. Well, that'll cancel and that'll cancel, so we'll be just left with mole per dm minus cube to power 1, which is mole per dm minus cubed. Like 10 to the power of 1 is 10. So mole per dm minus cubed. And then it says 2.4, state and explain the effect of using a high temperature and equilibrium yield of tetrafluoroethene. Well, we know that delta H is positive, so that tells me the forward reaction is endothermic, right? So if we increase the temperature, equilibrium is going to shift to the endothermic direction, and therefore what is it asking for? The effect on the equilibrium yield tetrafluoroethene, and which is that? Well, that's going to increase. So that's going to increases yield, or yield increases. The explanation, well, I'm going to type this up pretty quickly. Delta H is positive. That tells me forward reaction is endothermic. Equilibrium shifts to the right hand side, endothermic direction, forward direction, to oppose the increase in higher temperature. Equilibrium opposes temperature increase. That should be enough for 3 marks. 1 mark for this, and then 2 marks for equilibrium shifts to right hand side, and endothermic direction, forward direction opposes increases temperature, hence equilibrium opposes temperature increases. Equilibrium opposes temperature increase. And then 2.5, chemists provided evidence that was used to support ban on the use of chlorodifluoromethane as a refrigerant. Many refrigerators now use pentane as a refrigerant. State the environmental problem that chlorodifluoromethane can cause, and give one reason why pentane does not cause this problem. The environmental problem is that chlorodifluoromethane is going to causes ozone depletion / decomposition. Causes ozone depletion / decomposition. And the reason why pentane does not cause a problem, if you look at pentane, what's pentane? Methane, ethane, propane, butane, pentane, C5H10, right? C5H10. How many carbons? 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Not C5H10, C5H12. Of course, it's an alkane, so it's 2CN, H2N plus 2. The reason I showed this is because you can see here we only have CH bonds and CC bonds. Pentane, unlike what's it called, chlorodifluoromethane, pentane does not have Cl bonds, does not have Cl bonds, and therefore pentane cannot cause ozone depletion / decomposition, as pentane does not have C-Cl bonds, carbon chlorine bonds. And that is the end of question 2.